Hi everyone, Professor Heermans here with the second lecture part for Thursday, March 26th. In this lecture we're going to be covering desert environments, primarily playa environments, but also talk a little bit about lakes and Aeolian environments, and hopefully this will be useful in your Chidong Basin Lab number 1 that you started on Tuesday and is going to be due next Thursday. So what is a playa depositional environment? Well, playa consists of multiple parts. It's generally found in terrestrial, meaning landlocked environments that have a landlocked ephemeral or perennial lake, so a lake in a basin, and it encompasses the environments that make up both the lake environment but also all of the systems that feed that depositional environment. For example, where you have an alluvial fan that comes out of a mountain front, your alluvial fan comes out of the mountain front, and it brings sediment that's eroding from the mountains down into the valley. As soon as it hits the flat-lying valley bottom, it starts to dump its sediment. And of course, the coarsest grains get dumped in the alluvial fan, but then the finer grained material that is in suspension or in in the dissolved load make it all the way out to the ultimate depot center, which sometimes can be a lake environment. So the environments that you will find in a playa system include the alluvial fan environment, the sand flat environment. The sand flat is the distal part of the alluvial fan before it gets very fine grained, but after all of the coarsest material has been deposited. A mud flat, which isn't quite to the lake itself, but is really the edge of the lake, this red part right here. And then finally, the lake, either an ephemeral lake, which is there just part of the year, a perennial lake, which is there all the time, or you might actually have a lake or a salt flat, which is also called the playa proper. Now, living in the southwestern United States, there are lots of examples of playa depositional environments. This is an example from, I believe, the Owens Valley, and what you can see is that you've got the fans that are coming out of the mountains there, making it into the valley, and right between out in the valley, you actually have your salt flat or your playa. Call this the playa out here. And then between those, you have the mud or sand flat. And I'm going to describe the differences on how you would recognize whether or not you're looking at a mud or sand flat sediment. So for the purpose of this lecture, we're going to start in the lake and playa environments, and we're going to move back to the fan environments, which we discussed in the last section of or YouTube lecture number 1 of today's lectures. So the lake environments are found as these are typically thought of as the main depot centers, the main source, the final ending spot for any sediment that comes into the basin. Lake sediments tend to be very continuous and planar. They also are generally thin-bedded because as the water that's feeding the lake, it goes into the lake basin, and slowly the sediment suspends or falls out of the water column and creates these very thin-bedded layers. Oftentimes you'll find ripple marks related to wind layers, such as this layer down here. These ripples are related to wind at the surface of the lake, and sometimes you will get what are called varves, which are typically found where you have ice that forms in the winter and not in the summer. So when the ice forms in the winter, it shelters the lake from any new deposition. So you don't get any dust into the lake, and any layers that you get are very light. They're light in color. They're just it's just the finest sediment that's falling out of suspension. Now in the summer, when there's no ice at the surface to block any incoming dust, you blow a bunch of dust into this lake system, and you also have much more organic activity, meaning darker layers. So you get both light and dark. You get dark for the summer layers and light for the winter layers that are related to this cover of ice that's on top. So you get light, dark layers that are very typical of lake sediments in areas that have that freeze during the winter. Now, again, this is a great example of some lake sediments. You can see they're very continuous planar layers, and they also show repeated cycles that are related to changes in the lake level over time, where here we go from red to green to sand, hopefully this sandstone. Hopefully this is looking familiar to the last lecture, but again, this section is repeated. Red, green, sandstone, and related to overall drying of the lake, where the lake would get deep. So it's deep here. As it shallows, you start getting evaporites in the green layer, and then it completely dries out, and you get river sediments that are deposited in that lake flat, and then the whole lake basin rises, or the lake level rises again, probably due to some climate change, more precipitation in the area, and you start to get what are called these lake parasequences that represent changes in lake level over time. Some typical sedimentary features you might see in lakes include ostracods, which are calcium carbonate structures that form in very shallow water environments, usually shoreline environments where you have a tide that moves back and forth and back and forth, and these tiny little particles will accumulate calcium carbonate around them, and that's why they get these nice concentric forms. So this would be a lake shoreline down in this part of, when you form ostracods. Other types of structures are these convex upward structures. These are called stromatolites. These are algal mats that, again, form in very shallow water, warm lake environments. They're essentially algal mats. And these are some of the oldest sedimentary structures found in the world. They've been found over 1 billion years ago. But you can also find active examples of stromatolites forming in lakes such as Mono Lake in eastern California today. So they again represent these shallow water, usually saline lake environments. Lakes themselves, because they have changes in water depth, they're usually deepest in the middle, shallowest on the edges, do have different types of sediment that you might find in different parts. For example, in this lower section, you typically are going to have fans that feed into the lake. You then have your sand flat on the edge of the lake near the shoreline, and then in the middle of the lake you get your large continuous organic rich beds in very shallow waters or ephemeral lakes that only exist for part of the year at a time. A lot of times you might get evaporites forming. So I'm going to talk a little bit about evaporites. This is a photograph from Lake Manly in Death Valley. What you can see is this thick salt crust that's on the lake floor. And of course, this does fill with water periodically, and then the water dries out and precipitates out this salt. And we're looking up into one of the adjacent fans that are coming out of the Panamint Range just to the east. Now again, lakes can be both perennial, meaning always there, or ephemeral, meaning the water is only sometimes there. And so these playa settings, such as Lake Manly, where you get this salt crust, would be a great example of an ephemeral lake bed, because obviously the water is gone. Now these ephemeral saline pans or playa settings, these playa lakes that you're going to find in the middle of these valleys that have a lot of evaporites, typically have a cycle that they go through. And that cycle begins with filling the lake with floodwaters. And so you fill the lake, you cover the entire lake system, it brings all of these minerals from the surrounding mountain ranges into the lake basin. Then, after the storm is over, the floodwaters, because this is an enclosed lake basin, it doesn't have an outlet, so the only way to get rid of the water is to evaporate it. So then, second, you have evaporation. So this is the first stage. Second stage of evaporation, that begins to precipitate out these different minerals. They typically precipitate out in a particular order. Initially, the first thing to precipitate out might be calcium carbonate. Then you'll probably get some gypsum to precipitate out. And finally, the salts and halite will be the last thing to precipitate out. And that's why the crust that we just saw was typically from the most concentrated brines, and that was really the salt is left on the salt crust for the last stage. And then if you have a very wet year, it'll fill back up, and you start the whole cycle over again. So if we look at how evaporites are classified, again, there's the type of evaporite you get is a function of the minerals that are in the lake water. So, if you don't have any calcium or sulfate in your water, you're never going to produce gypsum. In fact, some lake basins you don't get gypsum, you might just get, say, calcium carbonate. But again, these are the different types of evaporites that you're going to find in lake basins. Everything from carbonates, so calcium carbonate, limestone, dolomite, to the sulfates, which the most common would be gypsum, and it's relative. Basically, if you take the water out of gypsum, you get anhydrite. And then finally, the chlorides, which are going to be your typical salts. And again, these are mostly a function of what the mineralogy of the water that comes into that lake basin, but also these do precipitate out at different concentrations. Halites tend to require the most concentrated brines, where gypsum and dolomite you can form in very dilute brines as well. So here's an example of some lake sediments. These are about 2.5 million year old lake sediments from the Chidon Basin. This is my former grad student, Hannah, who's now working as a professor at Appalachian State. But what you can see is we've got typical lacustrine muds with no evaporites at the bottom. This is probably the flooding stage of that lake basin. Then as it started to dry out, you started to accumulate more and more gypsum. All of these are gypsum crystals, but they're fairly well spaced. And then at the top, you get what's almost a pure gypsum crust, where the lake level was probably very low, it was a very concentrated brine. What we don't have is halite. But other parts in the basin, you can see, have those same sediments that grade up into these gypsum layers but are capped by this halite. Means this is a continuous drying sequence where you go from your flooding stage down at the base, and it continues to dry where you're precipitating mostly gypsum. The lake levels get so low, brines get so concentrated, you get a halite layer. Usually up above that, you might even get a fluvial sandstone, meaning it's completely dry, and then more lake beds on top as the lake floods and is filled up again. So you get these sequences of very consistent beds, but with changing mineralogy based on the lake levels. Now, adjacent to the Playa Lake Depositional Center that's out in the middle here and has these cycles that you see in the green and brown, adjacent to that you might get a mudflat. Now the mudflat is really, it doesn't have water for long enough to hold water where the concentration of the minerals can change to have these evaporite minerals. It's like the shoreline that floods every time there's a flood, but it doesn't hold any water. So all you really get are these fine-grained mud without the evaporites. So the mudflat are going to be mud layers. You're going to have ripples that are suggestive of some fluvial influence. You might get a lot of bioturbation because it's constantly getting wet, but it's going to be a lot lighter in color. It's going to be much redder in color because it's going to have evidence for subaerial exposure, where typical lacustrine beds, there will be parts where it's completely dried out, where you'll have evidence of mud cracks, but you're not going to have a lot of subaerial weathering, this nice red muddy color. You're going to get more of the greens and the organic colors of indicating that it's been underwater or subaqueous for most of its life. Here is a great example of some lake beds or a mud flat that transitioned to lake beds, probably as lake level rise, where these reds, where you can see there's some discontinuous sand beds in here that are probably fluvial channels. I would interpret this as a mudflat environment. The red color suggests subaerial erosion. There's also mud cracks in much of this area, suggesting it's probably not the lake depot center, but a lake shoreline mud cracks. But then these greens represent much more continuous, and there's evaporite layers. So this would be your salt flat or Playa Lake. So what we've done is we've gone from down section, we've moved from the mud flat up to essentially deeper water Playa Lake over time. Now moving from the lake to the dry mud flat to the sand flat is basically the distal fan. It is made up mostly of sand because you still have fairly high energy flows coming out of the fans, but they've deposited all of the coarsest grained, highest energy material up on the fan itself, and you get this fan apron. So you still get very continuous beds. These are some examples of mud flat, but they're very continuous, but they're fairly coarse grained. They're fine sand primarily to medium sand. They've got ripple marks. They've got evidence for mud cracking, and it's basically this fan apron that is, not quite the lake depot center, but really not a fan environment that has very discontinuous, clear channels, overbanks, levees that form in a typical fan environment. So again, this would be an example of a sand flat. You can see there's evidence for fluvial activity. We're not, the lake depot center is out here, and this could be, it can also be the center of the valley in these sort of terrestrial valleys, but it clearly has more of a fluvial dominated feel and evidence for a lot more fluvial activity than a typical lake basin. So this is really a nice take-home figure. This is the Green River Formation are about 50 million year old rocks that are found near Green River, Wyoming. They're right near the Uinta Mountains in sort of eastern Utah, but it's one of the most productive oil fields in all of the United States. And so there's been a lot of study, and what you can see is if you were to take a knife and cut it right through the Green River Formation, you would see that at between the mountains and the basin, you get what we'd expect, the alluvial fan material that grades into the sand flat, so these sandy would make great reservoir rocks, and then grades into really limestone, and finally you get halite and evaporites in the middle. So you get this perfect sort of Playa Lake setting, or the Playa Lake stratigraphy, where as you move from the mountains to the basin, you get very different sediments, very different sediment types from coarse grained to fine grained towards the basin depot center. And then as you go to the other side of the basin, you see you do the reverse. You go back into the limestone, then back into the sandstone, and then there's probably alluvial fans wherever the other side of the basin is. So that provides a pretty good summary of Playa Lake systems. Hopefully you've observed a lot of these in your lab number 2. Other parts, but of course, desert environments are more than just playas and fans. There are also a lot of wind types of sediments, such as sand dunes or even wind erosional features. These are called yardangs. This is sort of taking the aerial view. This is about, you can see in the corner, this is 5 kilometers, so roughly 3 miles. That means these dunes are roughly a mile across. There are lakes within these dunes, so whenever you have a dune system, they typically are associated with a shallow groundwater table, and oftentimes these interdune lakes that might appear. Dunes, of course, form as sand moves up the backside of the dune and then falls down the lee slope and continues to form these cross beds, and the backside of the dune continues to get eroded away, and so you end up with these nice crossbed sets that typically are on the scale of the dune, so a few meters high. give you some examples of that. You can see this is my student Josie. These are some nice Aeolian crossbeds in the bedding. This is also in China. This is the upper right figure up here. This is from actually Red Rock State Park in Las Vegas. But what you can see is this is about 3 meters tall, and these are big crossbed sets. These are old paleo dunes that existed in Las Vegas about 150 million years ago. Again, more examples of these big crossbed sets. So that's very typical of Aeolian sandstone. If you go to Zion National Park in Utah, you can see the scale of the tree down here. This tree is probably 30 or 40 feet tall. The beds, again, are going to be on the order of 2 to 5 meters. And what's really cool about these beds at Checkerboard Mesa is that they all have these beautiful crossbeds. And look, all the crossbeds are in the same direction, because crossbeds always form on the lee slope, the downwind side, meaning the wind direction didn't change for many thousands or potentially millions of years, and the wind direction was always from the east in this particular setting. When you look at stratigraphy of Aeolian fields, what you can see is generally you'll get thick sandstones with these thick crossbeds, but you'll also get areas where you might have ripples, or in this case lag gravels, where you have rivers that flow through these dunes. Or sometimes you'll get mud layers because you'll have lakes that are interbedded within the dunes. So you're never going to get just cross-bedded sandstone. You might get some lake beds interbedded in locations within these sandstones, and that's totally typical of Aeolian systems. So I'm wrapping it up here. But the sandstones that from Zion National Park and from Las Vegas, those may make up what's called the Nugget or Navajo sandstone. It was a giant dune field that covered most of the central U.S. for most of the Jurassic. The Jurassic ran from about 150 million years ago to about 210 million years ago. And so most of the sediments in the entire central U.S. are all these Aeolian sandstone beds. And what you can see is, even though there's big, thick sections of sand, sand, there are all these dune fields, there are also times when the area was dominated by either floodplains or even floodplains in here, or interdune deposits such as lake beds, because there's going to be other depositional environments in any one of these settings. So thanks for bearing with me. I know this took a little bit longer than I'd expected, but now I'd like you to just hit pause so you can use this figure, but you need to go into Canvas and take quiz number 2, where I ask you to identify these different types of depositional environments from the Badwater Basin in Death Valley. You can see that the Badwater is right here. If you want to go into Google Earth and Google Earth this to really take a look at these landforms yourself, I encourage you to do that. But I basically need you to match what these different environments are: Site B, Site D, Site A, Site E, Site C. There might be more than one answer to each one of these questions, but there are definitely some wrong answers. So do your best to match these. I expect you to get all of these questions right, and I will be happy to answer any questions about these either through email or at the beginning of class a week from now, next Thursday.